So yeah, I'm going to, as Carlos said, I'm going to kind of give a little bit of a background and kind of what it's a kind of a why do we need DSLs. I'm not going to answer that question. We're going to hopefully talk about that in future ones, but just kind of give a little bit of a background, and this can be captured in what people have called the 3 Ps: performance, portability, and productivity. So yeah, so I'm going to kind of go through each of these things: performance, portability, and productivity, and then kind of explain that, you know, we'd like to have all of these things, but there are issues about getting all of them at the same time. And then kind of finish up with where people are at the moment in trying to deliver these three things together. Yeah, so I guess the first question is on performance. Why do we need performance? And this will be obvious to many of you. Well, weather and climate modelling is a grand challenge problem, right? And the grand challenge problem is one where essentially no matter how many resources you've got, you need more to do more science. And you can think about doing more science in a number of different ways. The obvious one that people think of is obviously to increase the resolution. So you can see down here on the right, if you split your world up into lots of bits and you have a grid around it, as you get finer and finer resolution, you can resolve more and more detail, and therefore you can get a better and better model. If you look at this one, the UK doesn't really exist, and in fact, in all of them, down here you can probably see that, that the Mediterranean is landlocked. There's no water going through these things. So this affects the model, affects the accuracy. The higher accuracy you can do, the better the modelling is. So increased resolution is a very important one. So you need to do that. Another one is of course, as well as resolution, spatial resolution. You want to increase the time periods that you're modelling. Weather forecasts models are going from hours to days to weeks now, and you know, you go all the way up through to seasonal modelling, through to climate modelling, through to paleoclimate modelling. So there's an increase in time period that's always needed. So you need more and more compute for that. And of course, people are now going and looking at ensembles as well. That's running the same model with slight perturbations. So you need more for that as well. And another one is the increase in the complexity of the science, of course. So as you might start off modeling something with a very simple, maybe even just a constant, and then you have a small model for it, a bigger and bigger model, make it more and more accurate. So that needs more and more resources. And the big weather and climate centres, they're always trying to put more and more complex science in there. It's almost like a fight as to who can get their new science in, so they can increase and improve their part of it. And if you look at the top right, this is kind of an interesting historical perspective. So back in the kind of the 50s and 60s, you had an atmosphere model, and people developed their atmosphere model, and then people started maybe developing an ocean model independently, and then people said, okay, well, we want to link these two things together. You can't treat the atmosphere and the ocean model separately. We need to link them together. So another increase in complexity is not just increasing the complexity of the existing science, but also linking and bringing in together other things. And you can see here that there are lots of different strands that are shown. It's perhaps a bit too small for you to see in detail, but basically the idea is that we started with just an atmosphere model, and it's getting more and more complicated until we now have a full Earth system model that we're dealing with. Yeah, so that's one way in which the complexity of science is increasing as time. And I think it's clear that weather and climate is very important politically and economically. And so as a result, there are resources available to be able to buy some of the largest machines that are around. So they use the biggest machines. These machines are very expensive. And of course, we want to do the much science as possible, and we want to get the best out of them. And really, the best out of them is not really megaflops. Of course, megaflops is really good, but the important thing is the science per second. How much science are you doing per second on these big machines? And just to kind of give you a view of where the community is, kind of a big aim at the moment is to try and run operationally, looking towards in the near future to run operationally with up to one kilometre resolution. And if you split the world into 1 kilometre blocks, that's about 500 million squares. And of course, the world isn't, we're not flat, we can jump up and down. There's the vertical as well. And whilst most of these pictures, you'll see things are kind of flat because that's the way we think of things. Of course, they come out of in the vertical as well. And so they're actually cubes. And you tend to have a number of levels, maybe up to 100 or 200 or something like that. So I just multiplied that by 100. So you're under 50 billion squash cubes. That's quite a big problem that we're looking at. So just here's an example. So I work with the methods quite a lot. So I'm afraid my kind of slides tend to be biased towards them. But this is true for all the major centres. So the Met Office have 3 Cray XC40s at the moment, and that's 500,000 cores that they need to that are in there that you need to try and somehow keep busy with your computation. And one thing that is becoming more and more important is the amount of cost of electricity. So electricity is going up and up and up, and you can see that there's a 3 megawatt substation that's there to support this, and that's becoming more and more true. And this machine is just used for climate and prediction and weather prediction, ocean modelling, etc. It's dedicated to that. And they've been given last year allocated quite a large amount of money over the next 10 years to continue developing and getting new machines to continue this forward, going with increased resolution, better modelling. So the second P is portability. So of course we all want our models to be able to run on different machines, but really when we say portability here, it's more about performance portability. So being able to get good performance on different machines, not just be able to run them on different machines, but get good performance. So why do we care? If it's just one institution, historically, maybe it's one institution and one machine, then you could just simply optimize the code for that machine. And maybe you don't really mind about it being portable, performance portable. But these days, and in fact it's been true for a long time, models are used by a number of different institutions. They're shared, and those people will be using different machines. They'll have different compilers, different configurations. So it's going to affect other people. If you optimize for your machine, you may actually not help people on their machines as well. So you need to worry about that. And another thing is that models are really developed over a very long period of time, and supercomputers tend to be changed much faster than that. In some ways, you can think of software as being hard and hardware as being soft. And so you've got to be thinking about the next machine. If you optimize too much for your current machine, it's going to be quite difficult to roll those back and then optimize for the next one. And there is something that might sound a little bit flippant, but actually is quite an important thing. It's that if you can only run on one class of architecture and you're buying your next machine, then you're limiting your options. And the more limited in your options, the less likely the vendors that are selling you the machine are going to give you a good deal. And of course, the bigger machine you get, the more science. So you need to be competitive. And I think these days what that means is you need to be able to run on CPUs and GPUs. If you're just CPUs, then that means you're less likely to get a good deal. It's my personal opinion. Apologies to any vendors out there who disagree with that. So if we go on to productivity, well, these models are very large and they're very complex. So the unified model, which is the Met Office's current system, has around 2 million lines of code. And that's not just a static thing. The code is continuing being developed over time, over years, over decades. And it's not only developed by one person, obviously, it's many people in the institution, but also many people from different institutions. And even Alfric, which is the next generation model, is hopefully going to replace the unified model, and you'll hear a lot more about that over the week. That already has 10 to 20 scientists developing the code, as well as a core team of 5 to 10 and others external as well. So it's already quite a complex, large number of people. And to do that, we need to keep development time down as much as possible. And of course, you want to avoid bugs, and in order to do that, you need to have readable code. Obviously, you're going to have science bugs, but you want to avoid other types of bugs wherever possible. And really, the underlying point behind that is the code needs to be correct. And obviously, code needs to be correct, but in weather and climate, it's often used for critical decision making, critical forecasts and things. So it really is very important that that's true. So just a couple more points really on this. Domain scientists may not be performance experts, so you want to get science in there, but you also want to get it to be fast. So you may get some domain scientists that are both, but you may get some that aren't. And HPC optimization people may not be domain scientists, so they need to be able to interact with each other somehow. And of course, it's difficult to get a large number of people to work on this, because it's difficult to compete with industrial salaries. So if anyone out there is really interested in this and wants to get involved, I'm sure there are often posts available for people to come in. Little plug. So fundamentally, it's kind of a software engineering problem, really. So in order to support the scientists, you need to have nice development practices. You need to have an appropriate level of abstraction, and you need to make sure that things are supported with version control, coding standards, etc. Okay, so that's kind of the productivity side. So okay, so we've got these three things. What's the problem? I targeted this slide at the summer school, which I guess were possibly people who are slightly younger than the current crowd. So apologies if this isn't completely relevant, but I think we can all remember being students. And of course, what we want is when you're a student, you have good grades. But of course, you want to have a nice time, you have friends, you want to go out, have a good time. If you do both of those things, you're probably never going to sleep. So the question is can you do all of these things? I mean, no is the answer. You've got to make some trade-offs. Maybe you do a little bit less grades, maybe you do a little bit less social life, and then you just have enough sleep. One way to think about it is that if you have 3 glasses, maybe you've got enough to fill 2 of them. So how do you pour the water or whatever drink it is into the 3 to balance these things out? Do you just put all of it in 2 of them, or do you go for some sort of mix between them? What's your priorities? So just to continue this conflicting goals argument, so the top one is quite nice. So if you want to get somewhere really fast, you probably go in something like this. But if you wanted to take a lot of stuff from one place to another, you probably go in something like this. Very different solutions. And I think one of the main lines is if you want to get fast code, you may need to break some of these good software engineering practices that are considered to be helpful for code maintenance and development. And the problem is, of course, is if you optimize your code, it can be hard to understand and hard to extend. So just a simple example, we all know that if you're writing code, you want to make sure you isolate steps of an algorithm into separate functions. You don't want to repeat a function in multiple places. But in order to get the highest performance, sometimes you might want to inline these things and avoid these function calls. And because there can be a performance cost, the compiler can't do such a good job. So as a practical example, in the dynamical core in Icon, it's quite large. And one of the reasons why it's quite large is because the tridiagonal solver, which you'd normally think as being something you would put separate, is pasted into the function body. Now that's for performance, that's a choice. We take a hit in one thing in order to provide something else. Another example of conflicting is that if you want to get fast code for different architectures, and on the right here, I think we've got an NVIDIA A100 and the chip in the new Fugaku machine. If you want to do that, then if you want to get fast on these different architectures and you want to have performance portability, it might require multiple versions of the source code. So you might have to essentially have 2 different codes, one running on one and one running on the other. And the way people try and manage that sort of thing is often with maybe conditional compilation. I think riddled is a bit of a hard word. Maybe liberally spread might be a nicer way of putting it. with conditional compilation and directives. And that makes things harder and harder to test. And depending on what flags you've got, you have different coverages going through different routes. And again, if we take a look at the main function of ICON, but apologies, I'm not bashing ICON here. It's a very good model, but just an example of choices made. Inside that inner part of the code, there are 46 if-defs, conditional compilation, and over 400 annotations to support OpenAC and OpenMP. Of course, that hinders development. So what do institutions do at the moment? You've heard a little bit about what ICON does. Well, like I said, they make trade-offs between these things. And in some ways, the details depend on the institution. I have to say, these conclusions I'm going to put in my personal view. There are people here from ICON, people from the Met Office who may disagree with them, and feel free to write something in Slack or whatever, just to tell people if it's not quite true. But in general, I would argue that the Met Office has traditionally emphasised scientific performance, and that's kind of been the driver. And then they try and get the scalability and whatever once they decided on the scientific performance. Traditionally, ELFRIC is a bit different, but traditionally they've done that. And if you look at the NEMO consortium, NEMO is a well-used ocean model because it's used by lots of people around the world, particularly in Europe. They emphasise scientific performance as well, but also portability. And one of the things that they've done in NEMO, because they emphasise scientific development, is that NEMO is only run with MPI or in serial. It has no directives at the moment, so it won't run on GPUs. So that's the decision that, and people have done implementations of NEMO on GPUs and provided those, but it's not been brought in. So that's a decision for maintenance purposes. So that's an issue, and Andy will be talking a little bit about how we might get around that in a day or two's time. Whereas ICON, they've made a slightly different decision that runs both on CPUs and GPUs, but as I said before, that requires multiple directives, which can potentially affect maintenance. And they've gone for kind of what I would argue good performance, but not necessarily the highest, because they kind of try to keep the same source code as much as possible. So in general, I think if you look around, there aren't that many operational models that run on GPUs at the moment. Most of them are still CPU based. So a lot of people haven't taken that big leap yet. And people still quite a lot will optimize for their own architectures. Obviously they have to, and then other people kind of had to pick up the pieces. One area where there is some progress is you might say, so WARF was quite good at this. MPAS has some of this in it as well. Is where you try and make optimizations configurable where possible, and blocking is a good one, memory blocking or whatever, at the different levels in order to be able to do different things with different architectures without really having to change the code too much. So in summary, weather and climate models are large and complex, developed by large teams of people, used at multiple institutions, and need to be run on some of the biggest supercomputers. So we need these three things: performance, portability, and productivity. But these aims conflict with each other. And currently, institutions are making trade-offs between these. You can only have two amounts of your water for your 3 glasses. And typically, productivity, science development is usually the strongest driver, quite rightly. And so I think what we're going to argue over the next days is that actually one way to solve these 3 Ps problem and actually give ourselves more water is to use DSLs. DSLs are one way in which we might be able to address these 3 things without having to make so many compromises. And hopefully over this week, we'll see that that's true. And if you'd like to challenge that argument as we go along, please do, because this is we're very interested in all types of feedback. And I think that's me. Thank you very much.